Today we will be discussing about one equipment which is housed inside there. It's called nuclear magnetic resonance. It is again in continuation of IR spectroscopy, what we learnt on Tuesday. In fact, we have several other, for example, UV spectrometer and high resolution mass spectrometer. So, this I would say these four methods, analytical methods, IR, UV, NMR and HRMS. These four are very vital for characterization of molecules, and again to be little more specific, organic molecules. Okay. And of course, there were few questions after my lecture that day, that how we can use for your projects. So, again to describe, it is all about identification of chemical structure of any material, be it food, be it medicines, be it drug molecules or anything. I was giving one example, you guys study about fermentation. Fermentation means ethanol comes out. So, how to study how much ethanol comes out in your process. Okay. So, that is something you can do, because ethanol is another organic molecule which we can study. And in fact, all this, among these four analytical methods, I would say NMR is very, very important. Why it is important? Because you can characterize the molecule completely. This is important, because you see in IR, what we are talking, you cannot do the fingerprint region. You need to be an expert. Okay? And even if you are an expert, it is very difficult that you can characterize the molecule completely. In UV, similar, only you see the functional group which absorbs light, but this is something you can get completely, full identification of your molecule. And then you can use, I have been in collaboration with Professor Dwivedi in several of his projects. The same thing, we do characterization of organic molecules and study what your material, your food contains. Okay. So, now coming to this method, again I want to recall or remind you that in IR, I was telling about electromagnetic radiation, gamma ray, X-ray, UV visible, then IR, then microwave, then radio wave. And this is something where we use the radio wave, that means the lowest energy electromagnetic radiation. Okay. So, that is something enough for the characterization we are doing. Okay. Now, how does it work? Now, you can see something, if you give little bit side, here you see you should not take your keys inside, you should not take your watch inside, you should not take your phone inside, because we house one magnet. If you can see there, a tomb like structure. Can you see there? We will go inside and you can see there is a big tomb like structure. Inside that we have a magnet, very high power magnet. So, if we take things, then it will, I will show you also that how it attracts the iron or ferromagnetic substance. So, we should not take in there. So, now that is something is very, very vital for NMR spectroscopic method. Little bit about how it works. So, we know each atom is comprising of electrons, protons and neutrons. Okay. So, electrons are in the cells revolving around nucleus, and nucleus contains what? Neutron and proton. So, what is the charge of nucleus? Positive, right? Positive, because proton is positive. So, this is what deals with the nucleus, that is why it is called nuclear magnetic resonance. Okay. So, it is all about nucleus. There in IR, again I am comparing you, what was that? It was about the bond. Any bond you talk about, water, OH. So we were thinking that OH is like a spring and it vibrates. But here we are not talking about anything like that. We are talking about the nucleus. Okay. So now we understand that nucleus is positively charged. Okay. So one more thing is that electron spin, proton spin, neutron spin, if you remember Aufbau principle. Anyone remembers that? That two electrons in one subcell or in one orbital should be paired, means opposite spin. So that means they spin. So in the nucleus also the protons present, they spin, the neutrons present, they spin. So two protons, now they cancel each other's spin, two neutrons, they cancel each other's spin. So now in different atoms, let us say hydrogen, we have a nucleus. Hydrogen nucleus, what it contains? A proton, only a proton, no neutron, right? So hydrogen has one proton. Now one proton means it will not pair with anything because it's single. So now what happens? Because of the spin, now the any charged species, if it rotates, it will create magnetic field, right? So if the nucleus has non-zero spin like proton, like carbon 13, carbon, what is the atomic mass number? 12, mass number, yes, sorry. So how many protons, how many neutrons? 6 protons, 6 neutrons. So all of them pair. So now there is no total spin of nucleus. Little bit I am just telling, okay, which you can understand. So now carbon 12, which is present, if you take ethanol, it has got carbon, there is carbon 12. Carbon 12 will not be active in NMR. We cannot study carbon 12 in NMR. But what we study? Carbon 13, because carbon 13 has got one extra proton. So now that spin is the spin of the nucleus. Okay. So now any nucleus with non-zero spin, that means with either unpaired proton or unpaired neutron, it will be spinning the nucleus. So when it spins, because nucleus is always positively charged, all nucleus has got protons. So when it spins, it creates magnetic field, and that magnetic field will interact with this magnetic field. Now there will be two energy levels. If you again remember my slides, there was ground state, there was excited state. Always your molecule will remain in the ground state. It will take the energy, go to the excited state. And that is what we do there. The magnetic nucleus will absorb radio frequency to get excited. And once it absorbs, we will study how much it is absorbed. So that is basically the basic principle. Then there are so many other things. I teach whole semester to PhD students. So that means, because it is so vital that people have developed this NMR method, with time. For example, not only you can study your compound qualitatively. Qualitatively means what? Which atom it has, which functional group it has, but you can quantitatively also study. That means in your sample how much you have, and that is basically what we do in food process engineering collaboration. We quantify. So that means here you can see how much compound is there in your solution. Okay. So with this basic idea, we will now enter there and keep all your belongings which is having any metal outside. Okay, and please enter. Yeah, your watch, everything. So this equipment, of course there are so many types of this NMR spectrometer. We have got 400 megahertz spectrometer. I don't know if somewhere it is written. It's written there. Yes. So 400 megahertz, because that is the amount, or that is the energy of radio frequency we need while using this spectrometer for proton NMR. Proton means this hydrogen I was talking about. So that is what. And of course, if you have got 500 megahertz, Now even it has gone up to 1200 megahertz, and the more the capacity or the strength of this magnetic, inside this there is the big magnet. Okay, so depending on the strength of that magnet, the price is higher. For example, this one at present it will cost us 2.5 crores. Okay, and then if you go for this 1200 megahertz, I think it will be costing around 6-7 crores. Okay, of course they have got the advantage and depending on the money, but this is enough for us what we do here at NIT Rourkela. Okay, so now there is the magnet, but again that magnet is very, very sensitive. Okay, so if I explain this structure to you, you can see somewhere there is that green one, it is written nitrogen fill in. Okay, and then there is another one which is yes, that yellow one, you see helium. And now if you imagine this one, this is cylindrical, so there are many containers inside, and you can see the nitrogen is the outer more container. Okay, because it is almost close to the periphery. So what we do, we fill this from here to here with liquid nitrogen. There you can see these containers. I was talking there, the containers, they are all insulated cans where you can store liquid nitrogen, because liquid nitrogen, the temperature is minus 200 degrees centigrade. It keeps evaporating, but if you keep there, it stays for some time. So you can see the outermost can, cylinder, will have liquid nitrogen in it, and inside that yellow one, you can see that is after the liquid nitrogen cylinder, there we fill liquid helium. I don't remember exactly the melting point, but it is around minus 270 or 80. I could be wrong little bit here and there, but that is having melting point less than liquid nitrogen. So that means our magnet remains strong in liquid helium. But liquid helium is not, because liquid nitrogen is very much cheap, because we have got 70-80% nitrogen gas in air. So we have liquid nitrogen plant. I don't know if you guys are going to see that. So what we do, we just liquefy the the nitrogen gas. So that is cheap, but helium we don't have. So that's why helium is pretty expensive. So what we do, we fill liquid helium, and to slow down the evaporation of helium, we put nitrogen. And Subhadeep can tell you, this liquid helium we fill once in 6-7 months, but this liquid nitrogen we fill every week. And again, that is cheap, so we can afford that. So that is there, liquid nitrogen, then liquid helium, then inside you have the magnet. And these are the samples. Something it is getting solidified. I'll tell you about that one. Maybe this has to be liquid, this has to be solution. Okay, unfortunately something, probably the compound is not highly soluble, and some solvent got evaporated, so now it got solidified. But it has to be a clear solution, like I will show. Yeah, for example here. Okay, so this tube is called NMR tube. We need to make a solution. Okay, we take our compound, and then we don't have these solutions, this solvent, this deuterated solvents. I was thinking, if can we get tell someone, please bring them. Okay, so anything. Okay, so now what you need to make is take your compound and make a solution, and this solvent is not any solvent. It is actually any solvent, but for example chloroform. What is the formula of chloroform? CHCl3. But what we take here is CdCl3. That means we call deuterated chloroform. We don't take chloroform CHCl3. CHCl3 is very cheap. Okay, but when we have to buy CdCl3, we cannot use chloroform. There is the reason, I'll tell you. So all this, we have deuterated chloroform, we have deuterated acetone, we have deuterated dimethyl sulfoxide, all solvents almost what is used they have deuterated, and you will see the price of those solvents will go higher as you have more number of deuteriums. DMSO is 6 deuteriums, so that is very expensive than CDCl3. So like that. So what you do, you make a solution of your compound, you put in this tube. This is specific because inside it will go, we will show you how it goes. It will go there because any tube will not fit, so that will go, and then it will start there. As I told, there is the magnet. Here your compound has proton, so now they will have different level, and then we will see the spectrum there. Okay. Now some more accessories to, in addition to this one. This is one, what is this called? Automation. Yes, this is called, okay, the exact name means it is used for scanning your samples when you are not present. Okay. For example, one proton NMR takes 3 minutes. Now 3 minutes it is over, you have to put the second one. So somebody has to be here. But if we have this one, we bought it afterward, I think in 2015 or 16, we got this one. Before that, somebody was always present here to do. But now what we do, we have 24 sample holders. So we can put 24 and give our command there, so it will automatically scan one by one. So that's why our NMR machine works 24/7. We never stop it. Okay, so it always goes. So what happens here? We put our samples. Now you can see there is sensor. Okay, so and there is numbering here. So now if we give one command, there are different commands. If we give a SX, SX means I don't know the full form, but when you give SX 10, that means we gave the command, you take the sample from 10th holder. Okay, so it will take. Now when it takes, you see it has to push here, it has to push up the ear. It's not easy. Who will take there? So you need air pressure, and that's why there is something made a sound, that is the air purifier. Okay, so what we do there, again there is the one, this cylinder. So what we do, we push air, but that should be moisture free. We don't give air with, because air has moisture. So we have a filter which takes the moisture out. These are very sensitive methods, because moisture has got proton, right? So if we don't protect it, then our NMR will not be good, our spectrum will not be good. So that's why we make the air moisture free. So it is just a cylinder, you pass the moisture, there are substances which will capture moisture. So now it will be stored in the cylinder, pressure, with pressure, and that will supply here, and when we give the command, you will see it will push the sample up. And also when it brings here, if we don't have pressure, immediately it will drop, it will break. But with pressure, slowly it will come down. So these are all the processes we bring from there, that we create a cylinder with air pressure without moisture, and that makes this one working. Okay. Then we have got please there, that is called a console. Console means, see, here is the process, but now you have the detector, you have the recorder. So they all will make the information here. What information you get? Anybody? What information you get here? How much radio frequency was observed, right? That information will turn into a spectrum. Now you can see this is the spectrum here. You can please turn little bit. So this is the spectrum. How it will happen? Their radio frequency is observed, but that has to be modified into a spectrum which we understand, because we go through all this which proton which will observe how much radio frequency and so on. So from looking at the spectrum, we see that this is our molecule. Okay. So, that is what, but that this console that makes. Okay. So, that will upgrade everything, all these methods and finally give you the spectrum there. Okay. So, now we will put one NMR here, you will see what happens, and in that process also I will be talking a few more things. Any question by now? Anything?
What's
Yeah.
the difference between the small peak and the high big peak?
Yeah.
It is only for liquid sample. Solid sample?
Very good question. Yes. So, now you can see this is the solvent. You see it is written chloroform D. Okay, means chloroform means you will understand CHCl3, but it is not with proton but with deuterium. Now, of course, you can ask why. Because see, this is the solvent you are taking. Let us say you made the solution in here. You normally we take 10 milligram compound. Okay. So, in 10 milligram compound there will be protons, but if I take a normal chloroform, how much I am taking? This is around 0.5 milliliter. 0.5 milliliter means it will be around 800 milligram. So, I have 10 milligram compound I want to study, but I have taken chloroform 800 milligram, that has got a proton. So, now that proton will be a huge peak. Are you getting all? Because if I take proton solvents, I mean the solvent with H, then that proton will be a huge peak in comparison to the peaks for your compound. So, it will not be convenient to study this one. So, that is why these deuterated solvents are used. Now, she has a question that is it that we have to all make a solution? No. We can also study solid samples, that is called solid state NMR, and this is liquid state NMR. Okay. But our equipment does not have a system for studying solid samples. And now, but we know how it is done. There you take your, you remember again in our spectroscopy what we are doing with KBR. KBR we are mixing. Similarly here in solid state NMR we have some other solid which does not have proton. We need that always, and we mix our compound with that solid sample, and then we again put in a sample and put inside. It spins so high, it almost behaves like said liquid. Try to understand this one. The idea, because here what happens, see the magnet strength, the magnetic field has to interact with this. It is in solution, so it easily passes. But if it is solid, it does not. So, that is why it spins so high that it almost behaves like a liquid, and then it does. But our spectroscope, our spectrometer does not have that facility. That again increases the cost by probably 1 or 2 crores. We do not have that one because mostly this is fine. People have many, rich institutions, they do have solid state NMR, but it is rarely used. Okay. So
what if my sample is not soluble in CDCl3? Because as
we have other solvents.
As you mentioned, our samples solvents will be cost will be very high. So we cannot procure one sample and check whether my solvent.
No. Solubility you don't need to check with deuterated solvent. Okay. You check in protonated solvent. Normal solvent, because solubility will not differ.
Okay.
Because see, you are only replacing hydrogen with deuterium.
Yes,
so you don't never check the solubility in deuterium. This is pretty expensive.
Yeah, that's what I'm asking.
Just I can give example, because now we have provision for external sample. Okay. Once I was calculating, this much DMSO will cost me 250 rupees. This much DMSO. So that is how we are charging the outside samples, how much. Okay. So never check the solubility in deuterated solvent. You can always check the solubility in normal solvent.
So if my sample got solubilized in CaCl3, then it will get soluble.
Yes, in CDCl3. Otherwise, you check with DMSO, you check with water, you check with methanol, you check with acetone. There are all these solvents, deuterated solvents available. So once you see your compound is soluble in some solvent, you can use that deuterated solvent. Okay. Okay, so now we will do the whole process. Any of these sample we can start? Okay, so now just commands. This is very easy. You no need to remember or anything. Whoever operates. Okay, so now he gave the command. Which command? Which? Okay, so now whatever you see now, because see how slowly it is coming. If there will be no pressure, it will just dump and break. Okay, so now which one you are giving? SX, okay, 24. So now he will give the command to scan the sample number 24. Now you see what will happen, because it is all sensing the tube which sample holder is there. Now 24 means it will just continuously rotate, and at 24 it will stop. For example, this one cost us 25 lakh. This one, because so useful. Weekend, just give your sample on Friday, and Monday you come, all samples done. So this is very, very useful. Now 24 it stops. Okay, so now you see it will take the sample. Here we need the pressure, that's why. Then it goes there and drops there. The sample is going inside. Now you will see one tuck sound. Okay, so now it went to the scanner. Okay, and then something also, many times as how much solvent you need. Many people say almost this much, 3 fingers. Now why? Because when it sets there, this much it gives you the radio frequency. Now if you take this height, no use. Only it will scan this much. So this much you give. Sometimes you give less, it is okay, but better is this much, 0.5 milliliter. Okay, if you give, because their radio frequency goes, so that means whatever compound is present in this solution, this will be scanned. Okay, so now here again, like all one, you have to save your spectrum. So when you have to save, you have to give all this data. We give as date. In the date we have number. Then in the number you give your title, because in my name, my sample, your name, your sample. So all this will be done there. And then something, guys, you need to see here what will happen there. I think that is what we are doing here. Otherwise we can study in the seminar room. Okay. Now first you give log. Okay, just one by one. Log, enter. Okay, just don't do it now. So now first, once we put in there, we have to log the sample. Log the sample means we have to make the sample ready for scanning. Okay. So now how it is done? That I told you have to use a solvent. So now we give the command lock, LOCK. They have just specified. You give lock, it will ask you which solvent. Now you see we have all these solvents. Okay, it is all fitted there. You can also manipulate. You can change and other things. So now here we have this is in CDCl3. Yes. So you do CDCl3 and then okay. Now you see something here. This, yes, it will go down, na? We'll see. You can sit down, huh? No, why it is not going down? Is it hanged?
After giving top spin.
Okay, but log also it should go down. Okay, so now it will write that log is done. That means your sample is logged for the scanning. Okay, then what we do, there is a simming option. Simming means we try to make the magnetic field homogeneous for the sample. So now that's why we do this simming, and I remember in my PhD days we had manual spinning. We had if you go this, yeah, this one, BSMS, yeah, we had everything what is there in soft, in soft file, we had in hard file, like we had a like this system, and this one we had a button, like this fan regulator nowadays. So we keep spinning like this and try, please give that. But now, of course, advancing, science is advancing, you give this automatic, that is called top sim. That means it will sim your sample so well that the magnetic field in the sample will be homogeneous. Now give top sim, you gave? I think this one is hanged. You close this one. We will do it again, otherwise not a problem. This is hanged actually. पानी ଅଛି କି ଟିକେ ଦବ ଟିକେ. We need to show that top sim. Now, which one? This one here? Or but normally it should be here, no? Why this? There is some issue with this. Yeah, how to do? Or maybe we can restart. After this is done, we can do it. So you all are working in this food processing or something, some biotechnology also? Okay. So when do you think after learning all this you will use this equipment or no? Do you think? Yeah, of course, chemistry is very much applied in all fields, and what is that application is study of structure, chemical structure, because you all look at the properties of any matter or any structure, but we study the structure. In all my presentation at food processing, I always try to show that how the structure contributes to the property of your molecule. Okay, and then that's what when we study, we see that if the structure is vulnerable, if the structure is not stable, it will decompose. So that is what we do.
So how about sample preparation? How much mg of sample?
I'll tell you that. While it is going, we can talk about that. Okay, so now there was, but these guys all are in now?
No, sir.
I have to talk again? Or they don't need?
I guess they are waiting for the second batch.
Second, okay, we'll see if we will have time. But I try to come in. Maybe we can show this thing second time, because all these questions, it is better. We have, no? We have space. Guys, please come in, whoever are outside. Okay, so now he asked how much sample. Okay, so now just I'll again talk about ethanol, because probably if you see NMR spectroscopy in any book, first they talk about ethanol molecule. I don't know whether it is that molecule is so important. You know where is ethanol in all these drinks. Okay. So now talk about ethanol. I just mentioned there that carbon, because in our nature we have carbons everywhere. In that carbon we have two isotopes. One is carbon 12, one is carbon 13. Carbon 12 is 99% abundance. Carbon 13 is only 1%. Unfortunately, this 99% of carbon is useless here. When I take, let's say, 100 gram of carbon, 99 gram is useless. Our NMR will not read those carbon 12 nucleus. It will only do carbon 13. And that is, in 100 gram, we have only 1 gram. Baki 99 gram, whatever is there, it is all useless. But if you take proton, proton isotope, what are the isotopes of proton? Proton, deuterium, tritium, all of them are NMR active. And proton, which we study mostly, is 99.9%. Okay? So that means almost all protons are NMR active. They are sensitive. So that's why when you take proton NMR, it will take only 2 minutes, 2 minutes, 3 minutes. But if you take carbon NMR, at least you have to give for 2 hours. Getting my point? Why? Because if you take 10 milligram, all protons or 99% protons are sensitive. But only 1% carbon is sensitive. So we have different NMRs, proton NMR, carbon NMR, phosphorus NMR, fluorine NMR. So depending on the abundance of your nucleus, which is NMR active, you need either more sample or longer time. Okay. So if you have proton NMR, 10 milligram, 15 milligram is enough. Let's say you don't have compound. 2 milligram also is enough. 1 milligram is also enough. But 1 milligram you might need to do it for 40 minutes. If you have 10 milligrams, 2 minutes over. Okay. So the sample amount and scanning time depends on the abundance of the nucleus you are studying. Fluorine, phosphorus, they have isotope 100%. Fluorine 19, which we study here, that is 100%. Phosphorus 31, atomic mass number, that is NMR active. So for those NMRs, you just need 10 milligram, 5 milligram, 15 milligram, enough. But carbon, if you want to study, either you have to give more compound or you do the scanning for longer time. So what we do repeatedly, we collect the data and then merge it. So that's why this this automation helps us in scanning carbon NMRs during weekend. So we just put carbon NMRs, every NMR maybe 5 hours, 6 hours, something you will see 10 hours we do. Because we have whole weekend, 2 days means 48 hours or more than that. So we can easily scan 10, 15 samples. Okay. Okay, so now something you can see, the peak is coming. I will show you something, another version. Yeah. So you see that one is called an FID, pre-induction decay. What is that? Pre-induction decay is, I told, it will observe, if you remember that one. So 2 levels, ground state, excited. So when I give radio frequency, the nucleus will observe, go here, and once it goes there, it will not be stable. Excited state is never stable. When I stop the radio frequency, it comes back. When it comes back, it will emit the radio frequency, right? Whatever it has observed, it will emit. Now that is here, it is shown. See, this is time 0, very high peak. Now if this is all graphs. I can show you here, just expand any portion. These are all graphs. So what is occurring there? That if this is time 0, so first it emits, I mean majority of the nucleus will come down. Then with time, slowly it is coming down and almost nothing here. And how much time it is? Only 1 second. By the time it reaches 1 second, all excited molecules are down. Then what we do? We give another radio frequency. Then they observe, go to the excited state. Then we stop it. Then it comes down. Then we give radio frequency. So continuously we do that one. And as I told in carbon, we do it for 5 hours, 6 hours. We excite, let them relax. We excite, let them relax. So we continuously collect this emitted radio frequency. Okay. So now it is, we are all calculating, it is all done. Now we process the parameter. Now if you do there, yes. So now we got the spectrum. Of course, again analysis is major part, how we analyze. So what we do, I will just roughly tell you that we had taken the solvent, okay. So that one we take as the reference, okay, because it is known, when we took chloroform, I know we have taken chloroform. So there will be a peak for chloroform and I take that as the reference. And then all other peaks, you can see several peaks are coming here. That is all, so many things to learn there, but it comes according to the chloroform, according to the reference solvent, reference peak. So we take the solvent, we give the reference and then we try to analyze. Now you can integrate this. So you can see these values, these are called peak pickings, where the peak is coming. If you remember in IR, what was there? How we were studying the peak value, centimeter inverse, right? The wave number. Here, this is in a ppm, parts per million. We study in ppm, that is according to the strength of the magnet. Okay. So then this peak we study, you can see, there was single peak. It's like all these peaks. But here, something you can see here. Yeah, something you see, the peak is not a single peak. That's why it is called peak multiplicity. That means it doesn't appear as a single peak, it appears as a as a multiplet. That means the peak has got several peaks. In a single peak, you have got several peaks. That has also got the chemistry behind that, you can easily see depending on that one where it is exactly located. So that's why this method I told, it can characterize the molecule completely. Okay. Then you can do integration. Then I told we can quantify the peaks, and now you will do that. You can integrate all these, we will see. So you see this is 1, okay, this is 1, this is coming 2.8, this is coming 4.9, this is coming 0.89, you saw different values. What is that value? That is the relative area of each peak here. Okay. So, and what it says, that if you have 1 proton here, this has got 0.99 means 1 proton. You no need to think it exactly, you can always round up. Okay. So it is 1 proton here. 4.97 means there are 5 protons. So now you can see in IR you cannot do this one. But in NMR, you can always quantify that how many protons are present at a particular functional group. Okay. So this is all about proton. Similar thing about carbon, similar thing about fluorine. So whichever nucleus we study, we can easily quantify the number of those nuclei present in the functional group. Okay. So, that is why we can easily study. So, what we did first is you take the reference peak. According to the reference peak, always you go for the the value of each other peak, because yeah. So, here there was the reference peak. Now, and we know it is reported that chloroform peak comes at 7.26. So, if I give that value 7.26, now all other peaks will have their value. For example, this one is coming at 5.9, this one is coming at 4.6, this one coming 4.5. So, those are the ppm value for those peaks, okay? And that gives so much information about that one. First, that is there. Second is integration. So, once you integrate, you will see that how many nucleus, if it is proton, how many protons, if it is carbon, how many carbons, and so on are present in that particular functional group. So, that is there. You can show some carbon NMR. Yeah, so it is here in this carbon NMR. So, you can see, yeah. So, this is about carbon, and you can see, the baseline, it is not so good. There it was very flat, here it is not, because that is why the carbon abundance is so low. Okay. So, to get that proton like NMR, probably you have to do the same sample for 2 days, then you might get, okay, just because you have 99% useless compound there. Okay, you cannot have that one. So, that is there, and of course, then there are so many. You can show some Koji NMR, noisy NMR also. It is not restricted to this proton carbon NMRs. Now, there are so much advancement in this. There is 2D NMR. This is 1D NMR. We can have 2D NMR. This is one depth. Of course, you will not feel it. What is this? What is the difference between all that? But at least you should know that how you can apply or how you can use this equipment for your projects. And the use will be same thing, that if you want to study the chemical structure of the material in your project, then this equipment can be used. And what nucleus you study here? Hydrogen, of course, it is present in almost all molecules, carbon, fluorine, phosphorus, and so on. Yeah, this is you can see this is one 2D NMR, means 2-dimensional NMR spectroscopy. It is little different than that one, but it gives other important information about your molecule. Yeah, I think of course then we can always talk about how it is coming, but let us see any question from you all.
Sir, peak splitting is like triplet, duplet.
You know that, yeah. So, one proton NMR, maybe a small compound. We have, you can see, it is all, every day we are scanning, so many already data, very small compound. And now you can actually, I can show you. Okay, this is a very small molecule we have done. Guys, please. Yes, I think ethanol. Okay, so here I think maybe some other presentation we had make this ethanol. Okay, ethanol formula. What is the formula of ethanol? C2H5OH, or if I open it, CH3CH2OH. Okay, let's talk about that one. Now, I will make this one here. Now, you see a peak. How many peaks are there? Just how many peaks are there? 3 peaks. So, we call it a triplet. 3 peaks means triplet. Now, think CH3, CH2, OH. Remember structure. this, please go that triplet one. I think you will understand well. Beside going to how it comes, now let's see the application. The good that you asked. Okay. So this peak is for that CH3 proton. CH3 proton. Now it is coming a triplet, right? What do you think? Why it is coming a triplet? Okay, you can think that it has got 3 protons. That's why coming a triplet. Okay, go for the other one. You will find yourself that why these 3 are coming. Now you see there are how many peaks? 4 peaks. Okay, this is coming for CH2. Why it is coming 4 peaks here? It has got 2 protons. Okay, now think about CH3, it is a triplet. CH2, it is a 4 peak means we will call it a quartet. Now can you link something? CH2 4 peaks, CH3 3 peaks. So it tells about n plus 1, but that n is the neighboring nucleus. Because CH3 has how many neighboring protons? 2. Because CH3, then you have CH2. So there are 2 neighboring protons. So n, as he suggested, it is n plus 1. So that 2 protons, because there are 2 protons, it is coming 2 plus 1, 3. But when it is CH2, how many neighboring protons? 3 protons. CH3, CH2, after CH2 there is CH3. So 3 plus 1, 4 protons. So now exactly this multiplicity means the peak divided into how many number of peaks, that is called spin multiplicity, that depends on the neighboring protons or neighboring nucleus. If there are 3, it will come 4. If there are 2, it will come 3. If there is 1, it will come 2. It will be called a doublet and so on. Okay. So that is how. Very good. So you can see how much information. It not only it says which proton, but it says how many protons are next to it. That is another information. That's why it is very, very vital. It's like, we cannot live without it or our research. We need this equipment every day. Every day we are scanning probably 50 samples here. So this is the use. Not only it says how many protons, and then please do the integration there. There it is. So now you see this portion. Just highlight this portion here. Now you see here we have given 3 here, 2 there. What it says? What is this 3? I mean, you can see integration. Integration means area of that peak. So when we put this 3, this is coming 2. That means it says how many protons are there, because CH3 means 3 protons, CH2 means 2 protons. So these values, they tell you how many protons are present there, and this spin multiplicity, I mean the number of peaks in a single peak, tells about how many neighboring nucleus are present in the with respect to that particular peak. Okay, so that says. Yeah, that's a good question. Okay, yeah.
What kind of parameters can be determined by using NMR?
What kind of parameters? Okay. Can you please little bit explain your question?
Like what kind of properties?
Okay. Okay, I have a cross. I will answer your point. I want to understand your question. IR we studied. What kind of parameters we study in IR spectroscopy? Let's see how do you understand these parameters. Anything. Let's say in IR you understood the functional groups. Okay, the functional groups, because we studied that they vibrate at different frequency depending on this we discuss strong peak, weak peak, and so many things. So you find the functional groups in IR spectroscopy. Similarly here, the parameters what you say is if we are taking proton NMR, because there are different ways, different nuclei you can study here. Let us say you take proton NMR. So, in your compound, if guys please, if you take ethanol, you are taking proton NMR. So, what you get? How many different types of protons are there? Because different number of peaks, those many number of protons. In ethanol, you will get 3 peaks for CH3, for CH2, for OH. If you take methanol, you will get 2 peaks, CH3, OH. So, number of different types of nucleus. Nucleus means if you are taking proton NMR, you see different types of protons. You see carbon NMR, different types of carbons. You take fluorine and so on. Okay. First you see how many different types of nuclei are there. Second thing, those different nuclei, again for ethanol, 3 nuclei, but in what ratio? What ratio it was? OH1, CH2 2, CH3 3. So, when you take these 3 peaks, you will see in integration, one will be area 3, one will be 2, one will be 1. So, you see number of different nuclei. Second is you see each nuclei, each peak, how many nuclei are there. Like CH3, CH2, OH, you get 1, 2, 3. And third point is you see how many neighboring. For CH3, you will see a triplet. That means 3 neighboring nuclei. For CH2, you see 4 because 3 neighboring protons are there. So, like that. So, especially if you know that parameters is not the right word there, but what information you get is different types of nuclei which you can study. You can say, sir, why not oxygen? We cannot, because oxygen nuclei is not NMR active. We cannot study. Okay? Only proton, carbon, fluorine, phosphorus, those nuclei we can study here. In your sample, you can study how many are there, what is their chemical environment, and what is the what other nuclei is present in the neighbor to this nuclei. Done? Okay. I think we are also close to done. Okay, guys. So I hope I could demonstrate how it works, what is the importance of this spectrometer, and finally you think about your own project, that how you can use this equipment for analysis of your project. Okay, thank you guys.